Hello ladies and gentlemen, welcome back to Prospect Charter School's Algebra 1 course. Today we're going over section 6.4, Solving Special Systems. In essence, we are going over two very special cases in systems of equations where we either have no solution or an infinite number of solutions. Now to begin with, we're going to explore what might or might not have an infinite number of solutions, or just one solution, or, well, a whole bunch of other things that it could be. So let's delve into it and jump into our first example. Let's say that we are given the system of equations that looks like y is equal to x minus 1, and the other one is going to be negative x plus y is equal to 2. Now, if you remember from before, we have two major methods for solving this. We have the old-fashioned sub and chug method, or the substitution method, or we have the newer and more awesome Mender-Gauss elimination method. Today we're going to, of course, use substitution because one of our variables has already been solved for. So using the sub method, we are going to try to solve this system of equations. So for y, we plug in x minus 1. So that means for the second equation, which will be down here, we're going to plug in x minus 1 for y. So let's go ahead and write that down. We have negative x plus whatever my y is going to be is equal to 2. We're going to plug in this portion in red, so we plug in x minus 1 in red, and then we do our arithmetic. This should be pretty simple. Let's see, we have a negative x and a positive x, which cancel each other out, and I'm left with negative 1 is equal to 2. So, question for you. Can negative 1 be equal to 2? Well, let's look at the number line. Let's see. Alright, here we go. Here's 0, right? Here's negative 1. Here's 2. Are these two places the same place? Hopefully at this point you're saying, no, Mr. Neal, negative 1 can't be equal to 2. They aren't even the same number if we take the absolute value of it. And I say, you are absolutely correct. These cannot be the same. And since there's no variable, do we say x is equal to 2 or y is equal to 2? We can't say that either because there is no variable left. It all went poof. They all went away. So when you have a case in the end where you have an impossible situation, we know this is no solution. No matter what number I put in for my variable, I will not get both of these equations to be true at the same time. Never. So that's the no solution. So on the right, we're going to say note. If we end up in a situation with no variable, and two different numbers set equal to each other, then we have no solution. So make sure to put that in your notes. It might prove handy. It might be important. It might help you to not do bad on a test or a quiz or something else of that sort. We want to make sure that we know what we're talking about and know what happens when weird stuff occurs. So for this weird event, where we have a number that is obviously not equal to another number set equal to each other, we can happily say no solution. Now let's look at it in a little more detail. Let's look at another example. Let's say that we have y is equal to 2x plus 1, and 2x minus y is, y plus 1 is equal to 0. Once again, I think we're probably going to end up using the substitution method because one of our variables is already solved for. So using the sub method, I'm going to use the bottom equation in red, which is going to be 2x minus whatever my y value will become, plus 1 is equal to 0. And of course my y value in green is 2x plus 1, so we plug that in for the y, 2x plus 1. And then we do our fancy arithmetic. The negative gets distributed to everything on the inside of our parentheses. So on the next line I write down 2x minus 1 plus 1 is equal to 0. And at this point you're probably saying, Mr. O'Neill, there's nothing left. The 2x's cancel each other out, the 1's cancel each other out, I am left with 0 is equal to 0. So let me ask you another question. When is 0 equal to 0? At this point you should probably be saying, well, Mr. O'Neill, it's always equal. They're the same number. So of course they're going to be equal to each other no matter what. So if they are always equal to each other, what do you think this one's going to be called? That's right, infinite solutions. Or if you're really fancy, you take an 8 and you trip it and you call it infinite. Because 8's really full of himself. Anyway, so our next note. Note, if we end up with the same number set equal to itself, with no variables, then, can you guess what we're going to write next? Hopefully you said it. Then we have infinite solutions. This is another thing that you just might want to have in your notes. A little note that might save you hours of agonizing pain and discomfort, wondering whether or not you got that question right on the test or quiz or whatever it is that you were looking at. So make sure to have this one in there too. Which leads us to another conundrum. Why are they infinite solutions? Why are they no solution? What makes them the way that they are? Well, that comes down to parallel lines. If you remember, parallel lines are defined as lines in a plane that never intersect. And we discovered from this that parallel lines have the same slope. So, if parallel lines are lines in a plane that never intersect, can you solve a system of equations with parallel lines? Well, let's look. If I saw y was equal to 2x plus 1 and y is equal to 2x minus 1 as my system of equations, graphically speaking, we know that they're parallel lines. So let's call the top one green. Hello green, how you doing? And Mr. Green starts at 1, he has a slope of 2. And of course going the other way creates this beautiful pretend straight line, because we all know that if Mr. O'Neill ever draws a straight line, the world will end. And then the other one, again we're feeling a little festive, so we're going to turn it into red. And red starts at -1. It also has a slope of 2. And if we look at these two guys and ask ourselves, hey, when are these two pretend straight lines ever going to intersect? The answer is never, because they're parallel. So by solving the system of equations graphically, we can immediately say that this would be no solution because they never intersect. But if it was any other slope, if this was a -2 instead of a +2, they would intersect. If it was a 1/2 instead of a 2, it would intersect. If it was any number other than the exact slope of the other one, they would intersect and we would have one solution. But in this particular case, we have two distinct lines with the same slope. That means that they will never intersect. That means it will have no solution. But Mr. O'Neill, what about that one thing, the no solution thing? Well, I know you guys love writing no solution when you get lost, but let me tell you, it doesn't always work. Let's look at another system of equations. Wait, that was the no solution. What about the infinite solutions? My apologies. What about the infinite solution ones? Well, let's look at a system of equations that would have an infinite number of solutions. If we remember, we had y is equal to 2x plus 1, and we also had 2x minus y plus 1 is equal to 0. I'm going to use this same system of equations, only I'm going to take my bottom equation and I'm going to solve for y. In essence, I'm putting it into slope-intercept form, which seems to be everybody's favorite. So to do that, I'm going to add y to both sides and rewrite it as y is equal to 2x plus 1. Look familiar? That's right, they're the same equation. They're the same line. So if I have the same equation and the same line, how many times does it intersect? If you said, Mr. O'Neill, an infinite number of times, you would be absolutely correct. So if we're looking at the green line, green starts at 1, up 2 over 1, down to retreat 1, draw a semi-straight line. Do the same thing with red. Start at 1, up 2 over 1. I mean, if you look at these, I'm pretty certain that even when Mr. O'Neill draws them, they kind of intersect a lot. So, obviously, this would be infinite solutions. So if it's the same equation, repeated, it's going to be infinite solutions. If it's two parallel lines that are not the same equation, then you have no solution. And that, ladies and gentlemen, is that. The end of our lesson for today. So let's go ahead and look at our homework assignment, which of course isn't homework assignment, it's before you go work. So here's our bug work. And our bug work is going to be section 6.4. Hashtags, math rocks. Systems of equations is fun. Don't you love those graphs? Section 6.4, we're going to look at 1 through 11 odd, 13, 17, 19, 21, 25 because I love word problems and so should you, 27 to see how it works in other locations besides math classroom, and 29 because my job is to make you think. Alright, and that's it. Good luck and have fun.